All right, let's talk about one of the spookiest ideas in all of math, imaginary numbers. I know, the name itself is a little intimidating, but stick with me, because I promise, by the end of this, you're going to see that they're not some weird mathematical trick. They're actually an incredibly beautiful and, believe it or not, useful way of looking at the world. So, everything kicks off with this one simple little puzzle. Take a look. X squared equals -1. Now, if you try to solve for x, well, you hit a brick wall, right? I mean, think about it. What number, when you multiply it by itself, gives you a negative number? It doesn't seem possible with the numbers we're used to.
And here's exactly why that feels so impossible. You take a positive number, like 2 times 2, you get 4. Positive. But what about a negative number? Okay, -2 times -2, that's also positive 4. See the problem? No matter what you do, squaring a number on that good old number line always gives you a positive result. For hundreds of years, this is basically where the story ended, a dead end.
But here's the thing about math. A dead end is really just an invitation to invent something new. You know, we didn't just discover negative numbers lying around, we invented them to deal with concepts like debt. Same with fractions. We needed a way to talk about parts of a whole, so we invented them. This whole x squared equals -1 thing, it was just the next big problem that needed its own invention.
All right, so let's pull back the curtain and meet the solution to this impossible puzzle.
So what did mathematicians do? They basically said, fine, if a number that solves this doesn't exist, we'll just make one up. And that's exactly what they did. They created a brand new number, called it I for imaginary, and gave it one single powerful rule. I squared equals -1. That's it. That's the whole game. It's a new piece on the chessboard, a new tool in the toolbox, created for one specific job.
And just like that, with this one little invention, all these equations that were total dead ends suddenly have answers. You've got x squared plus 9 equals 0. Before, unsolvable. Now, the answer is just plus or minus 3i. It's amazing. But it also begs a huge question, right? What does 3i even mean? What is this thing we just invented?
Okay, this is my favorite part, because this is where I goes from being some abstract, weird idea to something you can actually visualize, something almost intuitive. It's all about rotation.
See, the whole problem, the reason this was so confusing for so long, is that we were looking for I in the wrong place. We were stuck on that flat one-dimensional number line that just goes left and right. But I doesn't live there. What I does is it creates a whole new dimension. It's like it says, hey, let's add a north-south direction to your east-west line. And boom, you've got a two-dimensional map, the complex plane.
So what does I do in this new two-dimensional world? Well, multiplying by I isn't just a math operation anymore. It's a physical action. It means rotate 90 degrees counterclockwise. Let's walk through it. Start at the number 1. You're pointing east, right? Now multiply by I. Flip. You rotate 90 degrees and now you're at I pointing north. Okay, do it again. Multiply by I one more time. Another 90-degree turn. And where are you? You're at -1, pointing west. Mind-blowing, right?
And that is the big reveal. The rule we started with, I squared equals -1, isn't some arbitrary math rule. It's just a description of a geometric fact. It's saying that doing two 90-degree rotations is the same as a single 180-degree turn. It's not imaginary at all. It's just geometry. And you can keep going. The powers of I just walk you around the compass points, north, west, south, and then, after 4 steps, you're right back where you started at east.
So there you have it. A problem that was literally impossible in one dimension, in algebra, becomes a super simple, totally intuitive action in 2 dimensions. I isn't just some made-up number. It's the language of rotation. Okay, so maybe you're thinking, cool trick, but what's it good for? Well, let's get to the payoff, because this is where this abstract idea of rotation proves to be one of the most practical, real-world tools that engineers and scientists have.
Let's start with something you're using right now, the AC electricity coming out of your wall. It flows in waves, and engineers working with it need to keep track of 2 key things at the same time. The amplitude, that's basically the voltage or size of the wave, and the phase, which is all about the timing of the wave. Now, you could try to track those as 2 separate numbers, but honestly, it gets really clunky really fast.
But guess what does the job perfectly? A single complex number. It's like it was made for this. The length of the number on that 2D plane gives you the amplitude. And the angle? That's your phase. One number, 2 pieces of information. It makes analyzing electrical circuits so much simpler. And get this, that imaginary part is describing a very, very real thing, the timing of the wave.
Okay, here's another huge one, the Fourier transform. Best way to think about it is like this. Imagine a complex sound wave is a smoothie. You've blended a bunch of fruits together. The Fourier transform is like a magic machine that can take a sip of that smoothie and tell you the exact recipe. Ah, I taste 50% banana, 30% strawberry, and 20% mango.
So how does it do that? It breaks down the messy signal into a bunch of simple, pure sine waves. Those are the ingredients. And how does it describe each ingredient? With a complex number, of course. The magnitude of the number tells you how much of that ingredient is in there, the amplitude, and its angle tells you the timing of that ingredient, the phase. This isn't just theoretical. It's the basis for how noise-canceling headphones work, how we compress images into JPEGs. It's everywhere.
All right, so if these numbers are so ridiculously useful for real-world stuff like engineering and audio processing, why in the world do they have such a terrible name? Imaginary? It's a totally fair question. And the answer? Well, it's just a historical accident.
Yeah, the guy we have to thank for the name is none other than René Descartes, way back in 1637. He ran into these weird solutions in his work, but he couldn't see the whole geometry and rotation thing. So he basically just dismissed them as useless, fictitious, imaginary. He literally meant it as an insult, like these things aren't real.
And unfortunately, the name stuck. It's a complete historical accident, like a fossil from a time when we just didn't get it yet. The name doesn't describe what the numbers are. It describes the confusion people felt back in the 17th century. And man, it has caused so much grief for students ever since, who hear imaginary and, naturally think it's not a real thing.
The brilliant mathematician Carl Friedrich Gauss saw this problem and came up with a way better idea. He suggested we call them lateral numbers. Lateral just means to the side. How perfect is that? It perfectly describes moving sideways onto that new dimension. He'd call positive numbers direct, negative numbers inverse, and these new ones lateral. It's a system based on what the numbers actually do.
So if there's one thing you walk away with today, let it be this. The only thing that's imaginary about imaginary numbers is the name. That's it. Forget the name for a second and just focus on what it does. And its job is to represent rotation. And that is a very real, very powerful job.
I mean, the journey of this idea is just incredible, isn't it? It starts out as this weird, abstract patch for a little math puzzle, and it ends up being a fundamental tool we use to describe electricity, signals, even the bizarre world of quantum mechanics. It's just a perfect example of how sometimes the craziest, most imagined ideas can turn out to reveal something profoundly true about our universe.
And that kind of leaves us with one last big, juicy question to chew on, doesn't it? If a type of number that we had to label imaginary turns out to be essential for describing the very real world around us, well, what does that say about the nature of reality itself? Kind of makes you wonder. Thanks so much for tuning in.